Hi, my name is Rabia Naseem and I'm PhD candidate at the Department of Computer Science. Thank you for attending my trial lecture. In today's lecture, I will provide brief overview of deep learning approaches applied to cross-modal medical image segmentation. First, I will introduce the basic concept of image segmentation. Then I will talk about some conventional segmentation approaches. After that, we will look at the concept of cross-modal medical image segmentation and the deep learning approaches proposed to solve this problem. These techniques can be grouped into two categories. The first category, single-stage training approaches, where the network is trained on multiple modalities simultaneously. And the second category, multi-stage training approaches, where the network is first trained on one modality and then retrained or fine-tuned on the other modality. Then finally, we will draw important conclusions from our discussion. First, let us see what is medical image segmentation. Image segmentation is the process of converting an image into meaningful regions, and this is based on some local property of pixels such as gray level, texture information, color, or shape information. So the process of segmentation in the image shown on top assigns unique labels to each distinct object in the image. As a result, we see different objects have been assigned different color, such as liver, spleen, and kidney, etc. Similarly, in the retina image, the vessel structure has been segmented from rest of the image contents after segmentation has been applied. Segmentation is very important area when it comes to medical images. It is used to separate regions of interest from the image. For example, in the image on top, tumor and edema has been segmented from rest of the regions in the image. Segmentation also serves as an input to biomechanical model. So we can see a vessel tree after segmentation has been provided as input to a biomechanical model, which is 3D model of human liver containing vessels and tumor inside it. Segmentation is also used to measure volume of different chambers in the cardiac MR images. There are several ways of doing segmentation, the most common being manual segmentation, which is done by an expert radiologist who marks the boundary of objects manually. In case of automated segmentation, the computer-based algorithms are used, which extract features from the image, and based on these features, an appropriate category is assigned to each region in the image. Semi-automated approaches combine both manual and automated approaches, where the segmentation process is initialized by a user, and then automated algorithms, rest of the process is completed by computer-based algorithms. Now let us see the conventional segmentation approaches. Conventional segmentation approaches can be divided into three types: thresholding-based, region-based, and edge-based. In thresholding-based segmentation, a threshold value T separates the image into foreground and background regions. The threshold value T, which is a fixed value, is compared with each pixel value in the image. So if pixel value is greater than the threshold value, that pixel is assigned to object category, and if this pixel value is less than or equal to threshold value, then the object is assigned to background category. So after applying thresholding, the input image is converted into a binary image carrying only two possible pixel values reflected by colors black and white. Some variants of thresholding-based segmentation approach have been proposed, such as ortho-thresholding, where instead of using a fixed threshold value, the value of threshold is calculated automatically. Region-based segmentation is also an important type of segmentation, where image is considered to consist of set of different regions. One of the simplest examples of region-based segmentation is region growing, where initial seed value is provided by a user. Then, based on a similarity criteria, which could come from gray level value or shape or color information, the neighboring pixels are grouped with this initial seed value, and the region expands in all dimensions. When this criteria is no longer satisfied, the region growing process stops. Edge-based segmentation is another kind of segmentation which depends on discontinuities in the gray levels of in the image. It detects edges and boundaries in the image and generally does not result in very good results. Although several segmentation approaches have been proposed, still segmentation is considered an ill-posed problem. Most common issues faced to segmentation algorithms are under-segmentation and over-segmentation. In case of under-segmentation, the segmentation provided by a computer-based algorithm constitutes only a fraction of the ground truth or reference mask provided by an expert radiologist. In case of over-segmentation, some extra area from background is also included with the foreground region, resulting in erroneous results. Vague object boundaries are also one of the important reasons that affect the accuracy of segmentation algorithms. Because segmentation is a very important procedure, its accuracy is very important. Machine learning approaches were proposed after thresholding and region-based segmentation approaches were proposed, and these approaches learn the relationships from data. Machine learning approaches consist of two phases, training phase and test phase. In case of training phase, the algorithm is provided with the training data and associated category to which this training data belongs. This is done by using feature extraction. Most common features that have been used are histogram of oriented gradient features, which basically measure the gradient magnitude and direction. Once the model is trained once the model is trained, it is tested on the unseen data, which makes the predictions on it. Deep learning is a class of machine learning which needs a lot of data. Instead of using handcrafted features, deep learning relies on multiple layers that extract progressively higher levels of features from the input data. The parameters of network are trained on this data, and the network is trained by gradient descent using backpropagation. Deep learning approaches can be divided into these types. For example, in case of supervised learning, a lot of ground truth or labeled data is required to train the network. In case of supervised learning, ground truth is not required at all. In the case of semi-supervised learning, labeled and unlabeled data both are used. And in case of weakly supervised learning, it uses noisy labels for training. Deep learning in general faces a lot of challenges when it comes to medical data, because the medical data comes from heterogeneous sources collected from different clinical sites using different scanning protocols and acquisition parameters. It is a bit challenging to train the network on this heterogeneous data. And then there are some privacy issues associated with this, with the data and deep learning. The data is not publicly available, and even if there are several publicly available data sets, the quality of data is not very good. When it comes to supervised learning approaches, it is very time consuming. It is a very time consuming task to manually label the data, and also every radiologist segments it differently. So every radiologist comes up with a different segmentation mask. UNIT is one of the pioneer biomedical image segmentation frameworks. It is basically an encoder-decoder architecture where encoder is responsible for extracting the abstract representation of data shown on the left, and decoder is responsible for taking this abstract representation and then generating a semantic segmentation mask. The skip connections between encoder and decoder are used to ensure better flow of information within the network. To facilitate the research community, several publicly available datasets have been provided for medical image segmentation, such as 1x1 dataset, which is a multimodal brain imaging data of healthy patients. Then there is another data containing data of Alzheimer's patients. Abdomen data is contained in the LITS dataset. Then there is another database, Cancer Imaging Archive, which contains data of several organs. In addition to public datasets, some hospitals and collaborative institutes also provide medical imaging data to facilitate the research community. Because segmentation is a very important problem, several global competitions are held to encourage the researchers working in the segmentation area to come up with more robust segmentation algorithms. For instance, S-Lever was organized in 2007, which used traditional segmentation methods. Then in the following year, machine learning approaches were introduced. In 2017, deep learning was also introduced along with machine learning approaches. And in 2019, all the methods presented in the chaos challenge were deep learning based. Multimodal images were also introduced in these global competitions. Then there were some segmentation challenges targeted to liver, such as ischemic lesion segmentation. It is also very important to assess the segmentation performance. So some commonly used quantitative metrics for segmentation evaluation are accuracy, sensitivity, and dice. Accuracy is a parameter which measures the percentage of correctly classified instances. Sensitivity measures the percentage of positive samples that have been classified actually as positive. Then dice score measures the overlap between the segmentation mask and ground truth. Now let us look at the cross-modal medical image segmentation. Multimodal medical imaging is used commonly in the clinical setting since it provides complementary information about the organ. Different imaging modalities are used to provide complementary information such as CT, MRI, PET scans, MRI variants such as T1 weighted, T2 weighted images. The multimodal medical images provide redundant information, which is particularly helpful in improving the discriminative power and also provide and are also very important to validate the opinion of doctors in diagnosing different diseases. Cross-modal medical image segmentation approaches with reference to deep learning can be grouped into two types. The approaches which take two modalities or multiple modalities and the network is trained simultaneously on both modalities. These are called single-stage training approaches. The other category of cross-modal medical image segmentation approaches fall in the category of multi-stage training, where the network is first trained on CT, for instance, on one modality, and then retrained or fine-tuned on the other modality, for instance, MRI. Then there is another concept of domain adaptation that I will introduce later. Now let us look at the single-stage training approaches. Single-stage training approaches are the approaches where model is trained on multiple imaging modalities simultaneously. These techniques can be grouped into three types based on at what level within the network the features are combined from the multiple imaging modalities, which are early feature fusion, late feature fusion, and layer level feature fusion techniques. In case of early feature fusion, the multiple images are concatenated simply as channels of the same image, and these concatenated images are then fed to the network. So the features are extracted from both images simultaneously, and these features are then provided to classification layer. Because the images are simply concatenated in this category, these approaches simply ignore the nonlinear relationship existing between the images from different modalities. Another method proposed using early feature fusion consisted of two steps: coarse segmentation and fine segmentation. In case of coarse segmentation, PET and CT were concatenated and fed to UNet, which generates a coarse segmented volume. Early feature fusion was done at the initial stage. Then, the coarse segmented volume was provided to adversarial network in the fine segmentation stage, where generator generates a mask, and this generated mask is compared with the ground truth by discriminator, and discriminator decides if the generated mask comes from real distribution or fake distribution. Based on this, the network is optimized. In this research work, the role of using multiple imaging modalities and its effect on the segmentation accuracy was measured. 4 quantifiers were used for this purpose. So looking at the results, we can see that the combination of PET-CT gives higher dye score and sensitivity values, which is also desirable when it comes to segmentation. When CT is used, the results are worst, and even with PET, the results are not as good as the combination of PET-CT. In case of average volume difference and Hausdorff distance, the lower value indicates better segmentation results. So when PET and CT combination was used, Hausdorff values are lowest for the PET-CT combination compared to CT alone or either PET alone. The second type of single stage segmentation approaches are late feature fusion. So in case of late feature fusion, the multiple imaging modalities, in this case MRI T1 and T2, are provided separately to the network, and the features are extracted from both modalities separately. The information from both modalities is combined only at the classification level or voting level. Because late feature fusion only considers higher level features of both modalities and do not consider the earlier or low level features, it also does not result in very good segmentation performance, similar to early feature fusion. Layer level feature fusion strategies were proposed to address the side effects of early feature fusion and late feature fusion, where the information from the multiple imaging modalities is not merged either in the start of the network or in the end. Instead, the information from all the imaging modalities is combined within the feature extraction phase. So in this work, cross-modality convolution combines information from all 4 imaging modalities at the feature extraction phase, and then it gives better segmentation results compared to either late feature fusion or early feature fusion methods. Hyperdense net is another form of layer level feature fusion, where the concept of dense connectivity was embedded with the layer level fusion. So dense connectivity in hyperdense net was not only provided within the single modality stream, but across the stream as well, to ensure better flow of information and better feature extraction capabilities. Because of this capability, the method was able to explore complex relationships between features of different modality within all levels of abstraction. Hyperfusion net is another method using layer-level feature fusion, which was proposed to address some of the disadvantages of hyperdense net. It proposed a res-fuse module which merge and normalizes features from multiple modalities, and it also introduced a combo loss which consisted of cross entropy and dice loss, specifically proposed to address the data imbalance problem. An interesting work, Octopus Fusion, compared the impact of using early feature fusion, late feature fusion, and layer level feature fusion, and concluded that with mid-level feature fusion or layer level feature fusion, the dice coefficient values improved in comparison with late feature fusion and early feature fusion. Also, the authors compared the role of using multiple modalities in comparison with single modality, and when the results were compared, we can clearly see that that irrespective of the feature fusion strategy, all the three feature fusion strategies or multimodal medical image segmentation approaches outperform the single modality segmentation approach. And this can be observed in case of both VGG16 and ResNet 50 when these two models were used for feature extraction. Now let us look at the second type of cross-modal medical image segmentation approaches, which is multi-stage training approach. When it comes to medical imaging data availability is an important consideration. Looking at statistics, we can see that the number of publications on a CT image and MRI were quite high compared to ultrasound image and PET, for example. It means the data of some modalities is widely available, whereas data of some modalities is not very easily available. In this case, we cannot use the early feature fusion, late feature fusion, or layer level feature fusion strategies. So what could be the solution in this case? Transfer learning. When we look at the feature distribution of two modalities, in this case MRI and CT, we can see that even reflecting the same organ, the features of the two modalities do not overlap, and we can see a clear disparity among the features of the two modalities. In this case, source domain refers to the domain on which network is actually or originally trained, and target domain is the domain on which network is fine-tuned or retrained. Because of this heterogeneous nature of data, transfer learning is not feasible, or even if it is applied, we can see the degradation in segmentation performance. So a possible solution proposed by some researchers is domain adaptation. The concept of domain adaptation is to train the network on label-rich modality and fine-tune it on label-lacking modality. Domain adaptation is a special case of transfer learning. However, some differences exist between transfer learning and domain adaptation. In case of transfer learning, the domain on which network is trained and the domain on which it is retrained or fine-tuned can be same or different. In case of domain adaptation, this is true as well. In the case of transfer learning, the task on which the network is trained can be same or different. However, in case of domain adaptation, the task is always same. So domain adaptation basically leverages knowledge learned on source domain containing more data and applies it to a different domain with less data. Domain adaptation approaches can be supervised or unsupervised. Let's first look at the supervised domain adaptation approaches. So one of the domain adaptation approaches used encoder-decoder network, and and two MR image variants, T2 weighted MR images and BSS-FP MR images were used to train the network for supervised learning. The network was then fine-tuned on another modality with only four samples. When the network was tested, it gave a very promising dice score of 85% on a huge data set. So the network, in short, outperformed a network that was trained from scratch. Another supervised domain adaptation approach was applied on unpaired CT-MR data. So in this case, CT and MRI data were taken from different patients, and the network was applied on multi-organ segmentation. Because of the unpaired nature of data, cycle GANs were used and combined with segmentation framework. Now let us look at the unsupervised domain adaptation approaches. So in case of unsupervised domain adaptation, the source domain data was annotated, whereas target domain data was completely unannotated. In one of the unsupervised domain adaptation approaches, cycle GAN was used again, and in this case, because of CT and MRI data were used, the researchers introduced an efficient loss function called tumor-aware loss. This tumor-aware loss function is able to retain the tumor contours better compared to cycle consistency loss. The results of the proposed unsupervised domain adaptation method were used with cycle GAN variants. So the cycle GAN results can be, and its variance results are shown in figure B and C, and the proposed unsupervised domain adaptation results are shown in figure D and E. From the dice scores, we can see that the results in case of tumor-aware loss, when it is applied either in the semi-supervised learning manner or in unsupervised learning manner, in figures D and E, the results are better compared to cycle GAN variants. Red line in the segmented images correspond to expert delineations, and yellow lines correspond to segmentations performed by the segmentation algorithms. When we compare the performance of D and E, which are the variants of the model that use tumor-aware loss, we can see that when the network was trained using semi-supervised learning, the results shown in figure E are better compared to those trained using unsupervised learning with no ground truth at all. Another unsupervised domain adaptation method, CIFA, was proposed, which basically combines image alignment and feature alignment in a single framework. The basic idea of this approach was to convert the source modality into a target-looking modality using image-to-image translation, and then feature extraction was done from this transformed modality and the target modality. The reason of doing this conversion or translation was to make sure, or at least to minimize the feature differences that could come up because of the different nature of source and target domain. In this case as well, GANs were used. The results of CIFA, or unsupervised domain adaptation method, were used with cycle GANs and also with supervised approaches. The results, even the qualitative analysis shows that the results of CIFA are better compared to cycle GAN and its variants. And when we compare the results of CIFA with supervised learning approach, we can see that supervised learning approach, because it is trained on a labeled data, results in better segmentation. The same pattern can be noticed in the dice coefficient values. So in case of CIFA, the value of dice in case of all the organs segmented shows better values or higher scores compared to cycle GAN and its variants. And on the other hand, when we compare the unsupervised domain adaptation with supervised domain adaptation, the supervised learning methods perform better than the unsupervised domain adaptation. Now let's conclude our discussion. So to sum up, in this lecture, we discussed different cross-modal medical image segmentation approaches, the two possible categories of these approaches where the network is trained simultaneously on multiple imaging modalities and where the network is first trained on one imaging modality and then fine-tuned or retrained on the other imaging modality. The comparison with single modality medical image segmentation approaches was also discussed. So in general, we have observed that the cross-modal medical image segmentation approaches have the ability to exploit redundancy and complementary information existing in the multiple imaging modalities. The cross-modal medical image segmentation approaches in general perform superior compared to single modality segmentation approaches. The concept of domain adaptation is a promising solution to address data lacking challenges. Also, the unsupervised domain adaptation approaches offer a way to address the ground truth scarcity problem. From the discussion and the research work discussed in this lecture, we observed that data of some organs is well represented, such as lungs and brain, whereas data of some organs, such as liver, is not well represented. It would be interesting in future to include some diverse loss functions, such as the tumor loss introduced in one of the research works, which is able to retain the structure and contours of tumors during the segmentation and image-to-image translation processes. Then there is a need to focus on unsupervised segmentation approaches more because of the ground truth availability issues. It would be interesting in future to integrate medical images and medical videos. And there is also a need to encourage sharing of medical data to facilitate the research community doing segmentation. Thank you for your attention.